Okay, in this podcast we're going to talk about how to use calorimetry to determine the heat of solution. So, what we're going to do is we're going to start off with measuring some amount of water and some amount of salt, ionic compound. You're going to be looking at a variety of them. And the way this is going to work is you're going to put the water in the coffee cup calorimeter and you're going to find its temperature. Okay? And then you're going to take the mass of this massed sample and you're going to put it in there. Okay? So you start with it empty, you add the salt into the solution, and then you measure the new temperature. So we're looking for that change in temperature. And the whole idea is that whatever the dissolving process is doing, the Q for dissolving, or the heat generated by dissolving, should equal the amount of heat gained by the water. Right? Now, if this is exothermic and it's generating heat, the heat will flow from the dissolving process into the water. Okay? So the idea is that by measuring how much energy the water absorbs, how much heat the water absorbs, we can determine how much heat is generated by the dissolving process. Okay? So that's the general idea. And in both cases, what we're going to use is, of course, we can use Q equals MC change in T, and that's going to be our value for water, for what the water absorbs. So we're going to assume that the entire volume is the mass of the water. Of course, water is 1 gram per milliliter in density, so 100 milliliters is going to be 100 grams. We're going to use the heat capacity for water, specific heat capacity of 4.184 joules per gram degrees C. And then we're going to use the change in temperature to determine how much heat the water absorbed, and therefore how much heat the dissolving process has produced. And then, of course, you can look at that heat and figure out how much heat per gram of solute or per mole of solute. And then you can compare different salts or different ionic compounds for how much heat they generate. Okay. So it's not exactly simple that the calorimeter, the coffee cup calorimeter, actually is pretty good at preventing heat loss, but some heat not only stays in the water, right, but some of it is absorbed by the calorimeter apparatus, everything involved in the calorimeter. So what you're going to do in the lab is a calculation for the heat capacity of the calorimeter. Okay, so the whole setup. And that's going to be some energy unit, usually joules or kilojoules per degree C. All right, so let me explain how we're going to do this. So what we're going to do is we're going to take some cold water, let's say 100 milliliters. You won't actually be able to use 100 in your lab because I don't think your coffee cup will hold 200 milliliters of water. So you're going to take some cold water, measure its temperature, right? Record it. And then you're going to heat up some other water, also 100 milliliters. You're going to take its temperature, and then you're going to add the hot water to the cold water. And you're going to look at what happens to the temperature. When does the temperature, take the temperature when it equilibrates, okay? Okay, so the whole idea is that the heat lost by the hot is going to be equal to the heat lost, or the heat gained, by the cold, okay? So in both cases, you're going to have Q equals MC change in T. And in both cases, if I have 100 milliliters of each, it's going to be 100 milliliters, which would be 100 grams, right, because the density is 1, times 4.184 joules per gram degrees C, which is the heat capacity of water, times whatever the temperature change was. And I'm going to do the same thing with the cold. The only thing that's going to be different with the cold is a different change in temperature. Okay? So, and these two values, theoretically, if I had a perfect calorimeter, should be equal. But you will find out that they're not equal. And the difference is going to be the heat lost to the calorimeter, which will allow us to develop the calorimeter heat capacity. So let's take a look at sample data. Alright, so I started with 100 grams of water. That was 22.5 degrees C. Then I add to that 100 milliliters of hot water at 47.6 degrees C. When they come together and equilibrate, I end up with a temperature, a final temperature of 34.8 degrees C. Okay, so let's take a look at doing some math. So first of all, let's just take a look at what to 34.8. Whoops. Cold, try it again, 22.5 degrees C to 34.8, which is a difference of 12.3 degrees C. The hot goes from 47.6 degrees C, and it also ends up at 34.8 degrees C. They end up at the same temperature, right, when they equilibrate? And that is a difference of 12.8 degrees C. Now, if I had a perfect calorimeter, they'd be the same. Okay. All right. So let's take a look at what we would do with this. So I'm going to use the Q for the cold, and that's going to be 12. So let's start with the math. So it's going to be 100 grams times 4.184 joules times 12.3 degrees C. This is over grams degrees C. And this is going to give us 5146 joules. I'm going to do the same thing with the hot. That's going to be 100 grams times 4.184 joules per gram degrees C times 12.8 degrees C. And that's going to give me a value of 209.5 joules. So what this says is that the calorimeter gained 209 joules in this process. So the heat capacity of the calorimeter is going to be the joules over degrees C. So the joules is 209.5. My degrees C is, I started it at my chain. I started with cold, and it went up by 12.3 degrees C. And so that is going to give me a value of 17 joules per degrees C. And that's how you do it.